All right, I'm going to go through these notes. Hopefully you read this section, so I'll help you try to make some sense of it. So we are in Chapter 8. We're talking about estimating with confidence. So the goal in many statistical settings is to use a sample statistic to estimate a population parameter. In Chapter 4, we learned if we randomly select the sample, we should be able to generalize our results to the population of interest. In Chapter 7, we learned that different samples yield different results for our estimate. So we, just like when we did the pennies, we had different p-hats or different x-bars for different samples. Statistical inference uses the language of probability to express the strength of our conclusions by taking chance variation due to random selection or random assignment into account. So just saying that when you select a sample and you get an x-bar, how good is it at predicting mu? So in this chapter, we're going to learn one method of statistical inference, confidence intervals. So we may estimate the value of a parameter from a sample statistic. So we might want to try to estimate mu from x bar, or we want to estimate p from p hat. As we do so, we'll learn not only how to construct a confidence interval, but also how to report probabilities that would describe what would happen if we use the inference method many times. What I want you to do right now is I want you to look at this investigation, and I would pause this video, take about 5 to 10 minutes, think about this problem and see if you can come up with some answers for it. It'll definitely benefit you if you actually pause the video and think about it as opposed to just looking at my answers. Alright, so the hope is that you pause the video. I'm guessing that if you were picking one value to estimate the actual number, you would have just used the x bar, which is 742. When you got to the point where you had to calculate a range, you might have gone about this several different ways. One way I think you may have thought about it is maybe if I said I wanted 68% within one standard deviation, how could I find that? Note here that I'm using 57 divided by the square root of 12 because 12 is my sample size. Since I'm using that x bar, I want to compare it to all the other x bars, so I want to use that standard deviation of the sampling distribution. You may have forgotten to do that, but I think the idea probably would have been the same. And you would have gotten this interval. Or you could have said 95% are within 2, and maybe you would have changed that 1 to a 2 and gotten this interval. Or maybe some of you would have approached it differently and said, okay, if I want to find the middle 95%, if I have 95% in the middle of my bell curve, I have 0.025 in each tail. So if I did inverse norm at 0.025, the mean, the standard deviation, or inverse norm at 0.975, the mean and the standard deviation, this would be my interval. So again, we're just coming up with intervals using something that we already know. So this is kind of like the idea of a confidence interval. So we're going to create an interval. So we're going to take our point estimate, and then we're going to add or subtract something to it, which we will call the margin of error. And then we're going to attach some probability to it, so we can say how confident we are. All right, so your basic. So again, if you had to give one number to estimate the unknown parameter, what would it be? So if you were estimating a population mean, you would probably use x bar, which is what you probably did in this last example. If you were estimating the population proportion, you would probably use p hat. In both cases, you are providing a point estimate of the parameter of interest, so you're just giving 1 point. So the definition here, so a point estimator is a statistic that provides an estimate of a population parameter. The value of that statistic from a sample is called a point estimate. Ideally, a point estimate is our best guess at the value of an unknown parameter. So x bar would be our best guess for mu. P hat would be our best guess for p. So what's the idea here? So back to that spicy chicken problem. So is the value of the population mean, so mu exactly going to be 742, the exact x bar? Probably not. However, since the sample mean is 742, we could guess that mu is somewhere around that. So we need to figure out how close to 742 is mu likely to be. So to answer that question, we asked another question. How would the sample mean x bar vary if we took many SRSs of size 12 from the population? So here we're just talking about that sampling distribution. So if I take all possible samples of size 12, find all those x bars, and create that distribution, how do those values vary? So if I just want to estimate the unknown mean mu, I use x bar as a point estimate. I don't expect mu to be exactly equal to x bar, so I need to say how accurate I think my estimate is. So remember that sampling distribution, so all of those x bars would follow a normal distribution with a mean mu and a standard deviation of sigma over the square root of n. And then I can use that curve like I did up in that problem to figure out an interval that will capture 95% of the x bars, or 90% of the x bars, or 99%, or etc. I can change that number. So my confidence interval, margin of error, or confidence level. So the confidence interval for parameters, so remember your parameters, the ones that we're going to deal with for the most part are mu or p, has two parts. So it has an interval calculated from the data, which has the form, the estimate, and our estimate is going to be x bar for mu, or p hat for p, plus or minus the margin of error. So the margin of error is going to tell us how close the estimate tends to be to the unknown parameter in repeated random sampling. So that's just talking about that distribution of x bar, or p hat. A confidence level C, which gives the overall success rate of the methods for calculating the confidence interval. So that'll be the second part when we give our confidence interval. Now that is in C percent, so if it's 90%, 95% of all possible samples, the method would yield an interval that captures the true parameter value. Alright, we usually choose a confidence level of 90% or higher because we want to be quite sure of our conclusions. The most common confidence level is 95%. But what might happen if we were 100% confident? So if you look at this cartoon here, the weatherman's going to talk about tomorrow's weather, and he says it's going to be between, the high temperature is going to be between 40 below zero, so negative 40, and 200 above. So Garfield says this guy's never wrong. So if you're 100% confident, you have to have a very wide interval because you want to make sure that you're correct. So that wide interval doesn't really add much value though, because I have no idea where the temperature is going to be in that wide interval. But another key part to all this is going to be interpreting confidence levels and confidence intervals. So the confidence level will be the overall capture rate if the method is used many times. So starting with the population. So imagine that we take many simple random samples of 12 observations. The sample mean will vary from sample to sample. We've seen this before when we did our pennies, when we did our BC's, PC's, etc. But when we use the method, so the estimate plus or minus the margin of error, to get an interval based on each sample, 95% of these intervals capture the unknown population mean. So if you take a look at this picture down here. So here is all the possible values of x bar. So this is my sampling distribution, like we did with our pennies, and I had you draw all those little x bars. So there's the actual mean. When I create an interval, so here's one interval, here's another interval, here's another interval, here's another interval. This fifth interval right here, so it comes, the x bar for this sample was right about here. So when we created an interval, it spanned that area there, and it didn't capture the actual population parameter. The other ones have all captured it based on their x bar for their sample. So when I say that I'm 95% confident, it just means that if I repeat this method many times, 95% of the intervals we create will capture the true parameter, so mu or p. It's mu in this case. So in this graph right here, there's 25 intervals. 24 of them capture the mean. So this implies a 96%, so we're very close to that. Remember, this percentage is coming from repeated samples. It's in the long run. So it implies a 96% confidence interval was calculated. I just did 24 divided by 25, and I got 0.96. So in these type of problems, we'll be asked to do two things. We'll be asked to interpret the confidence level, and we'll be asked to interpret the confidence interval. The level is just interpreting the actual level. So what does it mean to be 95% confident? So to say that we are 95% confident, it's shorthand for 95% of all possible samples of a given size from this population will result in an interval that captures the unknown parameter. So basically it's just saying if you repeated this process many times, 95% of the intervals will capture the parameter that you're trying to estimate. When we interpret the interval itself, so if we were trying to interpret a 95% confidence interval, we would say we are 95% confident that the interval from whatever number to whatever number captures the actual value of the population parameter, and we will put that in context. So we will go through an example here shortly. All right, one thing to note here. So interpreting confidence levels and confidence intervals. The confidence level tells us how likely it is that the method we are using will produce an interval that captures the population parameter if we use it many times. The confidence level does not tell us the chance that a particular confidence interval captures the population parameter. Instead, the interval gives us a set of plausible values for the parameter. We interpret confidence levels and confidence intervals in much the same way, whether we are estimating a population mean, proportion, or some other parameter. What is the probability that our 95% confidence interval captures the parameter? It's not 95%. Before we create the interval, we have a 95% chance of creating an interval that captures the true population mean. But once we have chosen a sample, found X bar, and calculated a 95% confidence interval, the mean will either be in that interval or not. All that's saying is if I go back here, all these intervals are 95% intervals. Or 96%. Before we create these intervals, we know that there's that chance of the value being in the interval. But once the interval is created, the actual mean is either in the interval or it is not in the interval. So there's no 95% probability that it's in the interval. It's either in it 100% or it's not in it. Unfortunately, we don't know which one it is, but we just know that we're using a method that 95% of the time we should be able to capture the mean. All right, so if we look at this example here, so we have, according to Gallup, on August 13, 2010, the 95% confidence interval for the true proportion of Americans who approved of the job Barack Obama was doing as president was 0.44 to plus or minus 0.03. Interpret the confidence interval and the confidence level. So I'm just going to go back here to this page. I'm going to do the interval first. So I'm going to say we are 95% confident that the interval from blank to blank captures the actual value of the population parameter, and I'm going to write it in context. So we are 95% confident that the interval from, so what I do here is I take that 0.44, subtract 0.03, I get my 0.41. I take my 0.44, add 0.03, I get my 0.47. So we are 95% confident that the interval from 0.41 to 0.47 captures the actual proportion, that's what I'm trying to estimate here, of Americans who approve of the job Barack Obama was doing as president. When I do the level, so I'm going back, how do I interpret the level? So remember, it's 95% of all possible samples of a given size will result in an interval that captures the unknown parameter. So 95% of all intervals from all possible samples of the same size, I don't know what the size is here, if I knew it I would state it, would capture the true proportion of Americans who approved of the job Barack Obama was doing. All right, I'm going to stop this video and you're going to have to go to the second video.